If you haven't caught wind of it yet, our solar system is currently hosting a visitor unlike any we've seen before. Comet 3 I/Atlas made its striking entrance onto the astronomical stage in early July 2025, first detected by the Atlas Survey Telescope. That's the Asteroid Terrestrial Impact Last Alert System, based in Rio Hurtado, Chile. Since its discovery, scientists worldwide have been racing to collect every possible piece of data on this mysterious interstellar guest, sparking a flurry of research papers, alerts, articles, and, naturally, debates. But in the midst of all the media hype, what do we actually know about 3 I/Atlas? Which facts are verified and which remain speculative or straight-up science fiction? In this video, we're diving into the latest findings on 3 I/Atlas, cutting through the noise to explore what makes this comet truly remarkable, just in time for its upcoming perihelion on October 30th. When I first covered 3 I/Atlas back in July, only 4 research papers had been published referencing it. Fast forward to September, and there are nearly 70. That's a staggering jump, reflecting a flood of new measurements, discoveries, and verifications that have dramatically expanded our understanding of this cosmic traveler. But before we explore the most recent revelations, let's quickly recap what we already knew. In my previous video, we talked about the initial detection of 3 I/Atlas and its designation as the third interstellar object to enter our solar system. We compared it to its predecessors, Oumuamua, which passed through in 2017, and Borisov, discovered in 2019. Unlike either of those, 3 I/Atlas is not only faster, hurtling through space at 58 kilometers per second, but also older, with age estimates ranging from 3 to 11 billion years. Since then, countless observations from telescopes across the globe have revealed more about this object. Let's start with Hubble. Observing time on the Hubble Space Telescope is notoriously difficult to schedule, with scientists submitting proposals months in advance. But Hubble reserves slots for targets of opportunity, unexpected events that require immediate observation. 3 I/Atlas qualified perfectly. On July 21st, when the comet was about 446 million kilometers away from Earth, Hubble captured stunning images that revealed its teardrop-shaped dust tail and streaked background stars, giving a clear sense of its incredible speed. These images allowed astronomers to estimate the comet's nucleus size at between 440 meters and 5.6 kilometers, significantly smaller than early estimates that didn't account for the coma. With ongoing observations, these measurements may be refined even further. Meanwhile, the James Webb Space Telescope joined the study on August 6th. Using its near-infrared spectrograph, astrochemist Dr. Martin Cordiner and his team investigated the comet's composition. They discovered a complex coma with varying outgassing patterns. Carbon monoxide and carbon dioxide appeared more active than water at that point, though this is expected to shift as 3 I/Atlas approaches the Sun. Surprisingly, some dust particles were being expelled toward the Sun, a counterintuitive effect caused by fragmentation and gas-driven acceleration. The comet may appear as a hazy glow from Earth, but up close, these processes reveal a dynamic and active world. Hubble and James Webb weren't alone in studying 3 I/Atlas. NASA's Transiting Exoplanet Survey Satellite, or TESS, typically hunts for exoplanets, but it also captures smaller objects, including comets. While the official discovery date of 3 I/Atlas was in mid-July, TESS had actually recorded it in images as early as May 7th. By stacking these images, astronomers could verify prior measurements and uncover new details. In September, Adina Feinstein, John Noonan, and Daryl Seligman published a paper using TESS data to measure the comet's brightness. Their calculations suggested a modest increase in flux due to its decreasing distance from TESS, but in reality, 3I/Atlas brightened far more than expected. Its energy output surged by a factor of 5 rather than 1.5. Observations from the TRAPPIST North and South telescopes confirmed these results, highlighting the comet's remarkable activity. Combining these brightness estimates with Hubble's nucleus size, researchers concluded that 3I/Atlas had been active even 6 astronomical units from the Sun, unusually far for typical cometary outgassing. This points to the possibility of highly volatile substances like nitrogen or hydrogen sublimating at great distances. Earlier, I mentioned that 3I/Atlas has a flatter light curve than Oumuamua, indicating a more even reflection of light across its surface. Feinstein's team, using TESS data, struggled to identify a definitive rotation period, detecting only faint periodic signals every 16 and 29 hours. Ground-based observations corroborate the 16-hour spin, giving us a clearer picture of the comet's rotation and shape. On Earth, telescopes have contributed further. On August 27th, the Gemini South Telescope in Chile captured multicolor images using the Gemini multi-object spectrograph. These images revealed both the comet's coma and its tail, which appeared longer than in earlier Gemini North observations from July. This confirms increasing activity as 3I/Atlas approaches perihelion. Spectroscopic analysis during this session also detected cyanide emission in the CN band, indicating hydrogen cyanide release from sublimating water. At over 3 astronomical units from the Sun, 3I/Atlas released around 8 times 10 to the 23rd power cyanide molecules per second. Measuring the ratio of dicarbon, C2, to cyanide suggested that the comet is carbon chain depleted, producing less than 0.09 C2 molecules for every CN molecule. Interestingly, Borisov shared this trait, hinting at potential compositional patterns in interstellar comets, though the sample size remains very small. Recent Polarometric studies also revealed something unique. On September 5th, Zuri Gray and colleagues presented the first ever polarimetric observations of 3I/Atlas, using data from Chile, the Canary Islands, and Bulgaria. They discovered a deep and narrow negative polarization branch, a light scattering behavior unlike anything seen in other comets or asteroids. This might place 3I/Atlas in a completely distinct category of small planetary bodies. Polarization tells us about dust grain sizes, surface structure, and coma shape, providing insights that traditional imaging cannot. Even amateur astronomers have contributed. During the September 7th to 8th lunar eclipse, enthusiasts in Namibia captured 3I/Atlas glowing green, potentially due to diatomic carbon C2 fluorescing under sunlight. While the comet's carbon depletion suggests limited C2, this observation could hint at increasing activity. Regardless, it produced a striking and mysterious sight visible even to non-professionals. Of course, no discussion of 3I/Atlas would be complete without mentioning Avi Loeb. The Harvard astrophysicist has stirred debate over the comet's size and origin, proposing that it might even be alien technology. Early estimates suggested a 10-kilometer radius, which Loeb argued was implausible for a natural interstellar object. Later measurements revised the comet's size down, though Loeb continued exploring his extraterrestrial hypothesis in a paper titled, "Is the Interstellar Object 3I/Atlas Alien Technology?" Critics, including AKM Yasanul Hake, have countered these claims, explaining that 3 I/Atlas's trajectory and acceleration can be accounted for by natural dynamics without invoking engineered maneuvers. This serves as a reminder. While speculation is enticing, data-driven evidence remains the foundation of scientific discovery. As of now, 3 I/Atlas continues its journey toward perihelion on October 30th at roughly 1.4 astronomical units from the Sun. While it will be too close to the Sun to observe at that time, it will re-emerge by early December, ready for renewed observations from Hubble, James Webb, Gemini, and other missions like SOHO, SPHEREX, and MAVEN. Questions remain. How will its activity evolve? Will it break apart? How long has it traveled to reach us? And where did it originate? Astronomers worldwide are racing against time to uncover these answers, and every new observation brings us closer to understanding this enigmatic visitor. Solving the mystery of 3 I/Atlas isn't just about glimpses through telescopes. It requires analyzing massive datasets, spotting subtle patterns, and constantly testing hypotheses. The comet moves quickly, but our pursuit of knowledge is even faster, and every discovery deepens our understanding of the cosmos.